Yeah, I think it's almost time. So maybe
whenever
should we
you're
start?
ready. I'm ready.
Yeah. Okay. First, okay. Let me give a brief introduction. Yeah. So today we are very pleased to invite Professor Robert Charity to this Fudan Open Seminar. So the Fudan Open Seminar is organized by the Institute of Modern Physics, the key laboratory of nuclear physics and ion beam applications. Fudan University and the Shanghai Research Center for Theoretical Nuclear Physics, NSFC, it's supported by the programming of introducing talents of disciplines to universities, the Journal of Nuclear Science and Techniques, and it's live streamed on Koshon.com. Today, we are a great pleasure to welcome Professor Robert Charity. So to those who are new in this field, let me give a brief introduction. So Professor Robert Charity is a distinguished researcher with a rich history in the field of nuclear physics. His academic journeys began with a Bachelor of Science in Physics with honors from the University of Queensland, Brisbane, Australia in 1980s. He went on to obtain his PhD in nuclear physics from Australia National University in Canberra, Australia in 1984, and he became a visiting postdoc research associate at the Lawrence Berkeley National Laboratory, and went to GSI Dempster as a guest scientist in 1988. Professor Charity joined the Washington University at St. Louis since 1919, and his work encompasses a wide range of topics focusing on the nuclear structure and the nuclear reactions. One of his notable contributions lies in the exploration of many for the effect within nuclei, particularly how proton configurations in calcium nuclei involved with the increasing number of neutrons. Throughout his careers, he has received several accolades, including the title of Fellow of Nuclear, the American Physics, and the Society, and the distinction of being an outstanding referees for the same organizations. So today, Professor Charity will talk about the adventures beyond the proton G prime towards the proton-rich edge of the existence of the chart of nuclides. So let's welcome Professor.
Okay, thank you, Simon. Let me get my talk here. Okay, and okay, and I'm going to get a what's the okay. Yes, okay, let me go back to the start. Okay, yes, it's good to talk to everyone, and very honored to be invited to give you all a seminar. So I'm going to talk about the chart of nuclides, and particularly this region here in light nuclei. So you've got the yellow and the blue and this red, they're all stable to nucleon emission. And in particular, I'm going to talk about these like pink colored guys. These are on the proton drip line, and you get pink colored guys on the other side. These are on the neutron drip line. And so these guys are unstable to proton emission on this side, or neutron emission on the other side. And every year around the world, I guess, like a handful of new isotopes are found. And generally, these are found in these extreme regions of either proton-rich or neutron-rich. And so very slowly, we're progressively moving further and further away from stability. And you might ask, well, when does it stop? Where is the edge of the chart of nuclides? So we'll address that a little bit. The other interesting reason for investigating this is these are all open quantum systems. So you have unbound, in this case, unbound protons. And so these should really be described as an open quantum system. So most of your regular nuclear structure models are closed quantum systems. We don't include coupling to the continuum. So we're providing data to test such models. And so that's another reason why we're doing it. So where would you think the edge of the chart of nuclides is? So, well, actually, I would say the edge of the chart is somewhat diffuse and may depend on what you define, how you define a nucleus. But basically, if I go back up here, as you move left here, the widths of these isotopes, or we call them resonances if they're beyond the drip lines, they increase, and eventually they just become so big that these states just sort of melt in the continuum. So what's the maximum width we can consider for a resonance or an isotope? It's interesting, in high energy physics, they have some very large widths, like the W boson has a width of 2 GeV, but such values are just totally unreasonable for a nucleus. So one thought is, well, just experimentally, finding these things, we create these resonances or isotopes in some reaction, and for them to be called a resonance or they have to have some lifetime so that then after the reaction they move off and then they decay. So you want some separation between those two steps, the formation and the decay. So you would like their lifetime to be greater than the reaction time scale. So what is the typical reaction time scale? So in the reactions we deal with, we have like 100 MeV per nucleon projectiles. And these are the projectiles that break up and create these resonances. And so reaction time scale, you can say, well, it's just the time it takes for that projectile to cross the diameter of the target, which is sort of this sort of time scale. And so if you look at what widths have time scales of this or larger than that would be decay widths of 9 MeV. So this is just based experimentally. I guess you could go to GeV per nucleon projectiles and even go higher. But I think the actual limit is somewhat lower in decay width. And that's because we're dealing with, these are resonances. They have some sort of periodic time scale associated with them. And you would like that periodic time scale, that would like them to live multiple periods of this time scale. Otherwise, it's difficult to consider it as a resonance. So what's a typical time scale for nucleonic motion? So you could say, well, I take a valence nucleon and it will travel from one side of the nucleus and back, and depending on how big the nucleus is. But anyway, in these light nuclei, that sort of argument says that the width should be less than 3.5 MeV. Experimentally, this may also be a challenge, especially if such a wide state sits on a very large non-resonant background. And as you'll see, we always have some background. And also may be problematic if the density of states is large, and they're all wide, and then they just overlap and form a continuum. So we will see. I'll show some examples. So let's start by telling you how we detect these resonances, these isotopes that are unbound to proton emission. So we use the invariant-mass technique. Same as used often in high-energy physics, for example, in the Higgs boson. And we have to detect all the decay products. So these things emit a proton or 2 protons, so we have to detect those protons, but also the residual. And most of the data is collected with this device. It's called HIRA. And there are 14 silicon, cesium iodide, E delta E telescopes. So for the invariant mass method, we need to measure the momentum of all the decay products. So the angle, so to get the directional part, is measured in these are silicon strip detectors. So they have strips on both sides. And from the position where they hit, we can get the angle. Silicon cesium iodide used as an E delta E telescope gives us particle identification. And then the energy is measured by the light emitted in the cesium iodide stopping detector. We're transitioning to a new detector system, done a couple of experiments. I'll only show one so far. And that's because when we get to heavy resonances, even when they emit a couple of protons, they don't get deflected much and the residual goes through this hole. So we start having low efficiencies. So we really want to detect it at 0 degrees. So that's why we've developed this. So we have, again, a silicon cesium iodide array, this time with an annular silicon. That's for the protons, but the residuals go through the hole and identified in a magnetic spectrometer. This is the S800 spectrometer at Michigan State University, where we do the experiments. And that also tells us the energy. We want a very good measure of the angle of the residual. So we have these crossed scintillating fiber arrays, which we use to measure the angle. How do we make these isotopic exotic isotopes? Well, we start with sparse secondary beams. So all the data is from the National Superconducting Cyclotron laboratory, these coupled cyclotrons. This little laboratory now is FRIB, and with FRIB we could do higher energy beams, but we have some approved experiments, but haven't done them yet. So we start with projectiles just inside the proton drip line. So as far as we can get in terms of proton richness, and still be stable, and so get it through the accelerator. So some examples of the beams we have: carbon-9, oxygen-13, neon-17, and magnesium-20. We always use a very light target, and that's because energy loss of the decay fragment, especially the heavy decay fragment in the target, is a major source of invariant mass resolution. So we can maximize the number of interactions we have in the target and at the same time reduce the energy loss by using a light target. And we use beryllium-9. We don't want to deal with a gas target like helium or hydrogen. Reactions we use, so well, if we just knock out a neutron from the projectile, and I'll show some examples for the oxygen-13 projectile. Knock out a neutron, you make oxygen-12. So you just cross the proton drip line and you get to the next layer's oxygen isotope. Then you can knock out multiple neutrons, for instance, to make oxygen-11. I'll show some data where we actually do a charge exchange. So we turn a neutron in the projectile into a proton. So we exchange that neutron from the projectile with a proton from the target. And we made thorium-13. You can also just pick up a proton, say thorium-14. That's beyond the proton drip line. And we're starting to look at more fragmented channels. So, for example, if you really fragment oxygen-13, you can end up with some strange things. So in this case, say you remove a proton and 3 neutrons from oxygen-13, you end up with nitrogen-9, and we can see nitrogen-9. And I'll show that as well. Our detectors probe very small angles. This angular region is dominated by projectile-like products in some sort of projectile breakup mechanism, whether it's creation of a resonance that then breaks up or direct breakup of the projectile. These products all have, at these energies, have velocities close to the beam velocity. We are dealing with peripheral reactions, not central reactions. So the target just helps break things up, but we don't see many target fragments. All right, so I'm just gonna start sort of a survey as we go away from the proton-rich line. So this is the region and the chart of nuclides we've been studying, and the so the black stable isotopes, the red are particle stable. They obviously beta decay, or but they don't emit nucleons. And so when you get beyond, first get beyond the proton-rich line, which is this black line here, you see you get one proton emitters and two proton emitters. So the one proton emitters are green. These are the known one proton emitters. And the known two proton emitters are yellow. You'll notice that all the one proton emitters are for odd Z nuclei, and all the two proton emitters are for even Z nuclei. This is just a consequence of the shape of the proton-rich line. Okay, so you notice the proton-rich line goes backwards and forwards, and this is associated with the pairing interaction. So if you have even number of protons, then the stronger binding, and therefore the proton-rich line extends further out into the proton-rich region. So wherever you start outside the proton-rich region and start emitting protons, you'll work your way down here, and eventually the first red square you hit will be an even Z nucleus. So if you start with an even Z nucleus, you must emit an even number of protons before you get to the next even Z nucleus. And so even Z nuclei beyond the proton-rich line must emit an even number of protons. This is just, of course, for the ground state. Once you start putting excitation energy in, you can emit more protons. And odd nuclei emit an odd number. So you can see that holds up pretty well. The other interesting feature is these yellow cases. These are the two proton emitters. These two protons just about always come out promptly. I mean, the two protons come out at the same time. For instance, this magnesium-19, you don't see a case where this magnesium-19 emits one proton and ends up into this state here, which then emits another proton. That's this quotential decay. Now, this state bypasses this intermediate state and decays directly to the red state. The simplest two proton emitter is beryllium-6, and it was discovered quite a long time ago. And I'll say a little bit about it. I'm not sure exactly when it was discovered, but the one thing of interest, once you start having a three-body exit channel, unlike a two-body exit channel, where the energy of the two products are constrained by energy and momentum conservation, once you have free decay products like a beryllium-6, which is the two protons to the alpha core, you can share the decay energy amongst the free fragments in different ways. So this is what I talk about momentum correlations between the free fragments. And to fully describe all the ways you can do that, you need a two-dimensional distribution. The first study of these correlations was in 1977. And then he measured one of these two dimensions. And in this case, they made beryllium-6 in a transfer reaction, and so they can infer in that reaction the velocity of the beryllium-6. But then they also measured the alpha particle from the decay. Remember, it decays by two protons plus alpha. And so then they could deduce the energy of the alpha particle that's this in the beryllium-6 frame. So as you see, you have some distribution. If the alpha particle has zero energy, that means that there was no recoil from the two protons. And so they came out back to back. So the two protons come out back to back. Their recoil to the alphas cancel. And this is called the cigar configuration. The other extreme is out here. This is called the diproton emission. And it's like as if the two protons were emitted as a diproton, though we don't consider diproton as a real resonance. But in any case, the two protons come out at the same angle, and this maximizes the recoil to the alpha particle. Back in 1977, they didn't have very good models to compare to, especially models predicting these correlations. So they did something simplistic. So this solid curve is just saying, well, the decay just samples the three-body phase space. And this actually is the best reproduction of their data, but it does fail in this region here. Of course, as the particles move apart, there must be some final state interactions. And they decided to include proton-proton final state interactions to get this dash curve, which was even worse. Obviously, they've ignored the Coulomb final state interactions. Anyways, these are just sort of toy models. The other models maybe was more serious, and that was this sequential decay idea, which I mentioned. So beryllium-6 is here. If it emits one proton, it's going to end up in lithium-5. Lithium-5 is way up here. Most of its line shape is energetically inaccessible. It's only this low energy tail that you could decay to, and then that would, and then lithium-5 would decay to the ground state of helium-4. Sequential two-proton decay had been studied many times, and there can be strong angular correlations between the emission of the two protons, especially in a case like this, where you start at a 0+ state and end at a 0+ state. So the angular momentum removed by the two protons, at least classically, is exactly opposite each other to cancel. And these strong angular correlations give rise to this strong oscillation in the prediction for the for this variable. And you see it doesn't, it's probably the worst reproduction of the data. So back in 1977, even though there was a possibility of sequential decay, it was ruled out by this measurement. The authors concluded that a better model is needed to describe their data. And that took 35 years. So, and that time, both the data and the theory improved. So I said that the correlations are explained by two-dimensional distribution. So this is a two-dimensional distribution. I won't tell you exactly explain what the parameters on the two axes is. This is in a representation called the Jacobi T system. And there's an equivalent representation that contains the same information. It's called the Jacobi Y. And so there's different parameters here, but they're based on hyperspherical coordinates. So these are the measurements for the correlations in the decay of beryllium-6. And this is the predicted theory by Leonid Grigorenko's group back then. And you see the reproduction of the correlations is extremely good. So we're at a stage where we can predict these things. There's one aspect of the correlations very easy to explain. And so imagine one of those dimensions I mentioned could be this axis, and that is the relative energy between one of the protons and the residual, or sometimes I call it the core, and that's divided by the total decay energy, okay? So if this is about 50%, that means the two protons had the same energy, okay? So each of them took away about half the total decay energy, ignoring recoil effects of the core. And you see, so that's where there's a peak. These extreme cases are where one of the protons rests and the other proton removes all the decay energy. And you see, there's no probability for that. So this is a hot collection of experimental data going from light to heavy for known two proton emitters from ground state nuclei. And you see they all peak at 0.5. And so the distribution around equal energy sharing becomes narrower, as you see for this very heavy, much heavier system. And there's an easy explanation. In fact, in 1961, Goldansky in his seminal paper on two-proton decay predicted this. And obviously, it's like you got to get two protons across the barrier. So to do that, you'd want to maximize the product of the barrier penetration factors. Okay, so it turns out if one of the nucleus is at rest, then the barrier penetration factor is essentially zero. So this is a minimum, and so the maximum occurs when the two protons have equal energy. And because these barrier penetration factors change much faster when you have a big Coulomb barrier, that gives rise to this much more narrow distribution as you go up. So this is a consequence of at least partially much higher Coulomb barriers. And theoretically, we can explain this quite well. So I have some theoretical predictions. This was the Grigorenko prediction I mentioned for Williams-6. This is also a prediction by the same group for neon-16 and zinc-54. And this is Simon, Wang's, and Vitek-Navarevich time-dependent model for oxygen-12. And as you see, in all cases, the data is well reproduced. I'll just show you one other case for two-proton decay. Oxygen-12, actually, we were associated with the discovery of this maybe in the late 1990s. Anyway, I guess maybe 10 years later, we did another experiment to get really good statistics. And so we start with an oxygen-13 beam. You knock out a neutron, you make oxygen-12. It decays by two protons plus carbon-10. We calculate the invariant mass of events that we detect, these three fragments. And this is the distribution in terms of the decay energy. And there's a very narrow ground state peak here. And there's some excited states. I don't have time to talk about the excited states. There's some interest in those. You can gate on the ground state. These are correlations, the blue histograms. Just concentrate on the top one. So this is the relative energy between the two protons versus the total decay energy. So if there's zero relative energy between the two protons, we're in this diproton limit I discussed before. And the maximum value up here would be in this, what I call the cigar limit, where the two protons come out back to back. And the prediction from the theory is in this red color. We've put that through a detector filter, which is done through a Monte Carlo procedure. So that causes some distortion from the theory, but it's quite small. And you see we reproduce the data quite well. So we understand two-proton decay. And there's some interesting nuclear structure you can learn from this, but I won't go into that. What I want to do is push further beyond the proton drip line. So what happens? So let's consider these odd cases. So they're green for single proton emission. If we try and push further out, then we can no longer just single proton emit one proton. For example, sodium-17, if we emit one proton, would land on a two-proton emitter. So it has to emit another two protons. So you go from one proton emission to three proton emission. You can see that in this chain of isotopes and this chain. And in this case, for boron-7, you go directly from a particle stable nucleus to a three-proton emitter. So the simplest case, again, would be boron-7, three protons plus an alpha. So it's like the beryllium-6 we described before, but now an extra proton. Boron-7 was discovered in 1967 in a three-neutron transfer reaction. So this is missing mass spectroscopy. They learn nothing about the decay correlations, but they do see a substantial peak. There's a lot of questions about exactly what the background is, and that gave rise to a lot of uncertainties about the width of the state, and there really hasn't been a better measurement since then, though I will show you some more recent data from us. So there's still a lot of uncertainty about the width of boron-7 and how it decays. I will show you some other ones. So the other two cases were measured by us, and they're created in charge exchange reactions. So this is oxygen 13, this square here. And if you change a neutron in the projectile into a proton by swapping it with one in the target, then you can charge exchange to thorium-13. And similar, this was from a neon-17 beam charge exchange to sodium-17. I'll just quickly show you the thorium-13. So thorium-13 would decay by 3 protons to carbon-10. So this is the invariant mass distribution we obtained. From this, there's this huge wide structure here. It's 10 MeV wide, so it's too wide to be a resonance. Possibly it's overlapping resonance, but some sort of background. But there's some structure here you see that's much narrower. And this is a fit, and our fitted width is like 1 MeV. And there was only one prediction. I think there's still only one prediction for this state. And that was from Fortune and Share. And this is their prediction for the ground state. And the first excited state, there's 2 arrows here because this represents the uncertainty of this second excited state. And you see this peak we see is indeed at the first excited state. What's interesting is we don't see any evidence for the ground state. So I don't know what's happening. Either we didn't create the ground state, or maybe the ground state is so wide that it's just part of this background. Maybe there's some other wide states that, and this background is just an overlap of very wide states, and there's only one narrow state. So we don't really know at the moment. There's further experiments needed. The other case, back up here, this case, we also didn't find the ground state. We also found an excited state. So this seems to be something to do with this charge exchange reaction. All right, so I talked about the odd Z nuclei transition from 1 proton emitters to 3 proton emitters as you went further out from stability. So of course, the 4p emitters have to do something different. So example, this case here, magnesium 19, 2 proton emitter, go to magnesium 18, now it's a 4 proton emitter. So obviously, the further you go away from the proton drip line, the more protons you have to emit. So that's pretty clear. And there are 2 cases, 2 known cases of 4 proton emission. Carbonates and magnesium 18. Carbonate, again, is the simplest case. We just, we start with the alpha and just add protons. So now we have 4 protons plus an alpha. So it's just 1 extra proton to the boron 7 that I mentioned before. Carbon 8 was discovered in 1974 with a missing mass spectrometry, so some sort of transfer reaction. And so they did not know anything about the correlations in the decay. So we did an invariant mass measurement to learn about the correlations. So let's just start with the lower panel here. So we create nitrogen carbonate, by a carbon-9 beam, and then you knock out a neutron, you make carbonate. So let's go back. So we start here, this red square, knock out a neutron, make carbon-8. It then emits 4 protons. Okay, so this is the invariant mass of 4 protons plus alpha. This is plotted now as excitation energy. So what we did is actually take a prediction for the ground state mass of carbon-8 and subtract that from the invariant mass we got. And that's why this peak is approximately 0 MeV. This is the ground state peak. It's not exactly at 0, which means the prediction we subtracted was slightly off. And so we have a new experimental determination of this mass. Here's carbonate. Here's 4 protons plus alpha. So does carbonate 5-body decay directly to here? Or is there some sort of sequential-like process? So, so remember, this was beryllium-6, and we said, well, we didn't sequentially decay. Beryllium-6 didn't sequentially decay through this state and down to here. You see, carbonate is very similar. It has a similar white state right next to it, same spin as the lithium-5. So one would kind of wonder whether you could really sequentially decay through this state. What you could think of is, if you're looking for a sequential decay, you would like maybe a narrow state. And the only narrow state is this beryllium-6. So the scenario we're thinking of is you underwent a prompt 2-proton decay directly to beryllium-6, and then you underwent a second prompt proton decay, leaving with the alpha residue. Okay, so the signature of that would be to find the beryllium-6. So remember, we do invariant mass, we have all the protons. If we had this scenario, if you took 2 of the protons, the last 2 protons emitted, plus the alpha core and found the invariant mass, that should give you the invariant mass of beryllium-6. Of course, we don't know which 2 protons they are. There are 4 protons in the event, but you can look at all the combinatorics. So starting with 4 protons, picking 2, there are 6 ways of doing that. And you take each of those 6 ways and calculate the invariant mass of those 2 protons in the alpha. And then you look to see if there's a beryllium-6 peak. And so that's what we've done here. So we put a gate on this peak here and constructed the invariant mass of the 2p plus alpha sub-events, that's what we call them. And indeed, there's a peak here. Now, to know exactly what shape this peak is, in the same experiment, we had a beryllium-7 beam, same energy as the carbon-9 beam. We knocked out same velocity, beam velocity as the carbon-9 beam. We knocked out a neutron, create beryllium-6, and then this is the invariant mass of the 2p plus alpha events associated with the decay of beryllium-6. And you see a nice ground state peak. So, of course, we knew the intrinsic width of beryllium-6, but this also includes the experimental resolution. Okay, so then interpreting this thing here, we can fit this with a peak of the same shape as determined from this beryllium-6 experiment. And if all the events did 2-proton decay beryllium-6, and remember, then only one of the 6 possible ways of choosing the 2 protons was correct, then that means only 1/6 of the events that we create by doing all the combinatorics is correct, that should be in the peak. So the area of this peak on top of this background, and the background comes from the other 5/6 of the events that are incorrect identification of the protons, this area should be 1/6 of the total. And it turns out that area is exactly 1/6 to a couple of percent. So that's telling us that we decay for beryllium-6 almost all the time, with maybe the possibility of a couple of percent something more exciting. So, and just to reiterate that, carbonate 2-proton decays to beryllium-6, which 2-proton decays to an alpha. So magnesium-18, that's the other case. So this is used with a different experimental configuration. So this actually was proposed by the group from Peking University. And they came and collaborated with us with our detector. And they took the data home and analyzed it. And so this is the spectrum they had for 4 protons and oxygen 14. Magnesium-18 was made with the magnesium-20 being knocking out 2 neutrons. And there's a very nice clear ground state peak. Some background, and then looks like the first excited state. And the this is the 2+ state. And then the location of that, there's some interesting information about the fading of shell effects in near n=8. But I don't want to go into that. So limited time. I was going to talk about the ground state. How does this one decay? Well, is it a similar scenario? Magnesium-18, 2-proton decay to neon-16. Neon-16 we've measured before as a ground state 2-proton emitter. We know it 2-proton decays to oxygen-14. You look, this does not sequentially decay. You notice this state here, going from a single proton to decay from here to here is almost the same as doing it from neon-16 in terms of the relative location of this intermediate state and its width. So one does not expect this to single proton decay to this state and then proton decay down. So is that true? So we can look at these subsystems again. So remember there's 4 protons in oxygen-14. We can just take one of those protons in oxygen-14, calculate the invariant mass and get the distribution, or 2 of those protons, or 3 of those protons, or in this case, just 2 of the protons by themselves. So these are the distributions you get, and the red curve is this scenario I just pointed out. It's a simulation of that scenario, and it reproduces the data extremely well. So that scenario, this scenario is consistent with what we see. So this seems to be a general feature of 4-proton emitters. They go through this 2 sequential steps of 2-proton decay. I now want to revisit boron-7. I said there was only one experiment from the 1960s. In the same experiment, we made carbon-8. We should also make boron-7. Okay, so we made carbon-8 with the carbon-9 beam, and we knocked out a neutron to make carbon-8, and then it decayed to 4 protons and alpha. We don't detect the neutron in our device. We can also have projectile fragmentation reactions where you, say, knock out a neutron and a proton, leaving you in a boron-7 resonance. That will decay and also leave you with the same channel. And most of the time, this proton from this first step, the projectile fragmentation step, it gets emitted at larger angles than where our detectors are at. So most of the time when we miss this, and we'll detect the 3-proton plus alpha event, and that will come basically from the decay of boron-7. However, there's some probability that we'll detect this proton and not detect one of the protons from boron-7 decay, and that would also give us a 3-proton plus alpha event, and that will give us some background underneath the boron-7 peak. However, it's this reaction that's the big problem. If we knock out a neutron and make carbon-8, of course we get this channel, but we don't always detect all 4 protons. In fact, most of the time we detect fewer than 4, and so there's actually quite a large probability we detect 3 of the protons. Okay, so then we're also populating the 3p plus alpha channel. When you can reconstruct these 3p plus alpha sub-events, they give a peak close to where the boron-7 peak is. So this is the data we see. So this is a peak, which is about where we expect boron-7 3-proton decay is. This is the background. As I mentioned, we expect background, but there's this big shoulder here, and that's from the events that we produce carbon-8, and then we only detect 3 of the protons. We could try and do a subtraction of these events, and we did actually publish a paper where we tried to do that. We believe there's a cleaner way of doing that. So this is the channel we're making boron 7. What happens if this proton and the neutron are actually bound? So that's in this scenario 3. You break up carbon 9 directly into a deuteron and a boron 7. Okay, then the boron 7 decays and you get a deuteron, 3 protons on an alpha. Okay, and then you just look at the 3 proton plus alpha events. Why is this better? Well, if you're worried about contribution from carbon 8 where you only get 3 of the protons, say you have a deuteron plus carbon 8, to get that, you'd actually have to pick up a proton from the target. So there are more, in such a case, there are more protons than in the projector. And picking up a proton at these high beam energies, the cross-section is very low. We do see such a thing, but compared to these fragmentation events, these are very low. So if you demand that you detect a deuteron in coincidence with your 3 protons plus alpha, you pretty much veto any possibility that you created carbon 8 in events and only detected 3 of the protons. So that's what we have here. These are events where we detect 3 protons, an alpha, and a deuteron. And then we look at the 3 proton plus alpha sub-events. And you get a nice peak here, sitting on background. How does this peak decay? Does boron 7, for instance, single proton decay to beryllium 6? So you can then look at the 2p plus alpha sub-events in these 3p plus alpha plus d events. And you see a nice strong peak which corresponds to the ground state of beryllium 6. And just to prove that these events come from this peak and not from the background, if you put a gate around this peak and then look at, and to demand that at least one of your 2p plus alpha sub-events is in this gate, then this spectrum goes to this. So basically you lose this background and you only retain the peak. So this is still in analysis, but it proves that at least there's a very strong decay branch for beryllium 6. In fact, most of the decay has to go for beryllium 6, and maybe there's some branch for some more exotic channel, but we're still looking at that. But basically, so I took this slide I showed previously. So this is now the boron 7 ground state. As I said, we know that most of the time it decays down to beryllium 6. So you see, the general idea is when you create these particles beyond the proton triple line, they like to decay directly down to the next even Z nucleus. Okay, so if it starts out of an even Z nucleus, two proton decays down here, but if it starts out with this odd case, it's just single proton decays. And then, of course, this is an even Z, it'll 2 proton decay to the ground state. So this is generally how we think these decays occur in these sequential steps of either 1 or 2 proton decay. Okay, can we go further? So I've shown you 2, 3, and 4 proton emitters. Can we go even further away and get a 5 proton emitter? So yes, we can. So we're just going to discuss the simplest case. So remember, we've been working our way up this line here, starting with an alpha particle. This was carbon 8. If we add another proton, we make nitrogen 9. So that would then decay by emitting 5 protons. So how do we make nitrogen 9? So we take this oxygen 13 beam, which I have talked about before. And if you do a projectile breakup, or if you like, in terms of knockout terminology, we remove 1 proton and 3 neutrons from the O13 beam, and then we would be left with nitrogen 9, which would then decay by 5 protons plus alphas. So we looked in this reaction for events where we had 5 protons plus an alpha. Indeed, we had quite a lot of events. I was actually quite surprised how many. There are no really peak-like features. Maybe there's some wide peaks here. So we tried to see if we could clear this up. And so remember, going back to here, we should expect this nitrogen 9 would be just to the left of carbon 8. We should expect it to single proton decay, right? So it should it should decay down to the next lightest even Z nucleus, which would be carbon 8. Just like boron 7 proton decays down to boron 6. So we decided to look in these 5 proton plus alpha events if there is a carbon 8 ground state. So again, each of these 5 proton plus alpha events, you take away 1 proton, you're left with 4 protons plus alpha, you calculate the invariant mass. And then you take away a different proton instead, and so there are 5 ways of doing this, and this is the invariant mass of all those 5 ways for all the events. And yes, there is a nice peak at the carbon 8 ground state, and the red curve is a fit with some background and the known parameters of carbon 8, including experimental resolution, and it reproduces this data quite well. So we put a gate around this, and we demand that at least one of these 4 p plus alpha sub-events is in this gate. And then we look at the distribution we get for 5 protons plus alpha, and it's these red data points. So basically, we've lost all the yield above 10 MeV. And what we have left is a somewhat more narrow structure, and it actually kind of looks like 2 peaks. So maybe we're forming 2 peaks of nitrogen 9. However, especially in cases like this, where these would be wide peaks, we have to be careful about the background. All right. So what are the backgrounds? So as I said, we can have O13, remove proton and 3 neutrons, create nitrogen 9. Sometimes a proton could be bound to some of these neutrons in a deuteron or triton. Doesn't really matter. The nitrogen 9 decays by emitting 5 protons, and if this one is a free proton, we'll get a 6p plus neutron plus alpha. We don't detect the neutron. This proton typically gets emitted to a large angle, so if we did make nitrogen 9, we have a good chance of detecting, well, the probability of detecting these 5 protons is small, but most of the time they would come from decay of nitrogen 9, and not from cases where we missed one of the protons in nitrogen 9 and got this proton from the initial step. However, as we said, we found events where we have a proton plus carbon 8. You can create carbon 8 by another scenario, that's 2. In this case is you break up the projectile, and now in terms of 2 protons plus 3 neutrons and carbon 8. And so if you detect the decay products of carbon 8 in one of these protons, that will make a p plus carbon 8 event. Okay, so that's what we found here. These are p plus carbon 8 events. So do they come from this scenario, or do they come from this scenario? So we decided to look at another channel to get some idea of what these backgrounds look like. So this is a somewhat simple case. This is carbon 10 produced by fragmentation reaction in this oxygen 13 beam, and it produced 2 protons plus 2 alphas. And just like in our case with nitrogen 9, we can look for an intermediate state. In this case, we looked for boron 9. So we looked at p 2 alpha sub-events. And the invariant mass spectrum of that, there's a very sharp peak corresponding to the ground state of boron 9. It sits in a region with no background. You can gate on this extremely cleanly. And this is the invariant mass distribution you get from such events. And it has narrow peaks sitting on a broad background. So this is the sort of background we're interested in. How do we know what the background looks like? Well, these projectile fragmentation reactions have been studied many times, and there are no strong. So if you produce the proton boron-9 and projectile fragmentation reaction, we expect no strong correlations between this proton and the decay products. And so to create a distribution where there's very little correlations, you can do a technique called event mixing. So you take one of these events and a second one of these events, and you take the proton from one of these events and the boron-9 decay products from the other event, and you put them together and you calculate the invariant mass. Okay, and so you do that from many such pairs of events where the pairs are chosen randomly. And that will produce a distribution where the proton and the boron-9 are random, uncorrelated, I should say. And that's this dotted curve. And it reproduces the shape of this tail, which is largely from the background. However, it does, and that's how I normalize it. I normalize this distribution to get the tail right. And it gets the energy dependence very well. But clearly it fails in here. There's just way too much yield. And the reason is this event mixing technique has ignored important correlation. So if we created the proton and the boron-9 in the first step of reaction, not from the decay of carbon-10, then they would be created somewhat close together, maybe not directly adjacent, but they would have some Coulomb repulsion. And so this Coulomb repulsion will repel events where there's small relative energy between the proton and the boron-9. And so that's what we're seeing here. There has to be some suppression of these events due to this Coulomb correlation. How do we know what the correlation should be? So we looked at events when we now added a deuteron. Yeah, we like adding deuterons. Another thing about deuterons, they don't come from the decay of proton-rich nuclei. Proton-rich nuclei like to proton decay. They don't like to emit a neutron-rich deuteron, or for instance, a triton. So if we have a proton, a deuteron, if we had a deuteron, this deuteron came from the first step breakup, projectile breakup. So if we look at the correlation between the deuteron and the boron-9, we should just see this Coulomb suppression. And this is the correlation function we reconstruct between the deuteron and the boron-9. And so at large relative angles, the correlation is 1. It means there's no correlation, but at small relative energies, correlation becomes small, and this is just a suppression due to the Coulomb correlation. And if you use the triton instead of the deuteron, you would get essentially the same distribution. So the idea is that all hydrogen isotopes for the promptly emitted hydrogen isotopes will all have the same correlation function. So then if we're trying to construct the background, what we do is when we mix events, we weight those mixed events based on the proton-boron-9 relative energy. So if this has a relative energy of 2, we go up here and say, okay, that's 0.7. We weight that event by 0.7, and that produces this suppression. Okay, it's a little complicated, but that's how it works. And it works very well for this carbon-10 case. This suppression comes down here. You can fit these data based on the known widths and centroids with this shape of background. So for the proton carbon-8 events, we do something equivalent. And we can get the shape that we expect for the background. And that's this dotted blue curve. So the question is this red curve, this is our experimental proton plus carbon-8 invariant mass spectrum, can that be reproduced by this thing? So I've normalized this blue curve to be about the same peak height as the experimental data. And as you see, it's just too wide to explain the experimental distribution. However, we have low statistics. And you could say, well, given, Poisson statistics in producing this, is it possible just for fluctuations that you could produce a distribution like this red distribution if your intrinsic distribution is given by the blue. And this is the same question they had in the Higgs boson. They knew what the background should look like, and they had to ask whether the peak they saw for the Higgs boson in the invariant-mass spectrum came from fluctuations in the background or came from a real peak. So you can do a fluctuation analysis. And if you remember in the Higgs boson, for discovery, they had to be, the fluctuations had to be at the greater than the 5 sigma level. So we actually come up to 4.8. We're just shy of at least the threshold for discovery, at least in hydrogen physics. In fact, the editor of Physical Review Letters told us we couldn't claim a discovery. So anyway, so if the background can't explain this distribution, then that means there's need for nitrogen line decay. A more reasonable normalization of the background is this dashed blue curve. It reproduces the high energy tail region and the low energy tail region. And there's a region in between where you have contributions from nitrogen 9 states. So I'm going to show you some fits to this distribution. So this was the red histogram I just showed. Now it's data points and the red curves of fits. So I said it could be a doublet or a singlet. So the top panel is a fit with just a single peak. So our matrix line shape includes experimental resolution and the background that we determined from this previous discussion. The fit gives you a width of 2.3, so it's approaching this limit of 3.5 MeV, which we're trying to ascribe to the limit to the chatter nuclides. However, we believe it's more likely to be a doublet. And one of the reasons is, of course, theory tells us that there should be 2 peaks there. So we asked the theoreticians who could deal with this situation the best. That was Simon Wang and Vitek Narovevich and company. They have a gamma shell model, so that treats the continuum, the coupling between the continuum and the bound states. And they predict that in this region here, where we see possibly 2 peaks, there are in fact 2 states. And one state is almost exactly here, and that's a 1/2 plus. And the other state is almost exactly here, and that's a 1/2 minus. And they're predicted with some more reasonable, not so close to the limit. We think this is a better reproduction of the data. Unfortunately, given the statistics, if we're trying to fit 2 peaks plus a background, and in this region with the peaks, there are only 1, 2, 3, 4, 5, 6, 7, 8 data points, but we have like 7 parameters to do such a fit. You can't really constrain all the parameters. So we really can't constrain the widths. So another possibility shown by this histogram is where we just force the width of the ground state to be very wide. In fact, really approaching the limit of what you might think for a resonance. And you can sort of fit the data. Probably chi-squared is a bit worse in this case. Of course, what we really need to make a definite statement on this, in fact, whether there's 1 peak or 2 and what's the width of the peaks if there are 2, is more statistics. If we had more statistics, we could have smaller bins with smaller error bars, and we could fit these parameters. So that's something for the future. But we see these nice peaks. Another reason we like this bit compared to this one, in this case, there's almost no background. And if you look at the neighboring nitrogen isotopes, they have like 40% background. So it seems very strange you would make this very exotic nucleus almost purely without any background. So this situation with the 2 peak fit is more consistent with what we see with the neighboring nitrogen isotopes. And so this is the decay scheme. So we have possibly these two peaks, and a proton decay to carbon 8, which two proton decays, proton 6, which are two proton decays. So I'm almost at the end, and I'll just one more slide. Are there other 5 proton emitters? Are there 6 proton emitters? Well, you know, it's easy to find candidates. You just have to start at a bound nucleus and then say if you want a 6 proton, a particle bound nucleus, and you want a 6 proton emitter, you just add 6 protons, 1, 2, 3, 4. That would take you up here. So if you could make this silicon isotope, and its width is not too large so that you could actually identify it, it would be a 6 proton emitter. But this is a bit too far from the proton drip line. Actually, if you start here and knock out 2 neutrons and create this guy, this is a 1, 2, 3, 4, 5, 6. This would be a 6 proton emitter and possibly reasonable width. Unfortunately, even with FRIB, we're not going to get enough beam of this, at least in the immediate future, to do this experiment. And I'm sure you can find other cases if you go to heavier nuclei. So let me just summarize. So we've explored way beyond the proton drip line. And as you saw in the case of nitrogen 9, this allows us to do tests of structure theories that take into account the open quantum nature of these nuclei. So we're testing the role of continuum in nuclear structure. And as you see, as we get further from the proton drip line, we just start emitting more protons. And if we get even further away, we'd get more protons. And we expect to see more such things as we go up. I believe we're pretty close to the extreme proton-rich region for these light nuclei. Maybe in some of the cases we could go a little bit further, but I really can't see us going much further. Remember the nitrogen 9, we're already at widths about 1 MeV in some of the other cases. Finally, I just mentioned the collaborators. So the work I showed has all been done by people working with me from Washington University, and there's my longtime collaborator, Lee Sapatka, and a lot of the experiments were thesis projects of various students. And our experiments are all done in collaboration with Bill Lynch, Beijing, and now Kyle Brandt's moved to MSU. This group, and Alan Wisma from University of Connecticut has participated in many experiments. We've had great theoretical support, not just for nitrogen 9, but in terms of the 2 proton correlations from Simon, VTEX groups. One of the experiments was, as I mentioned, was a collaboration. Peking University, and they proposed and analyzed the group. So that's where I'll stop, and so I can take questions. Hope it wasn't too long.
Yes, thank you very much for this long and very interesting talk. So now it's question time. So if you have questions, please unmute yourself or raise your hand. So any questions from audience?
Yeah, may I? So I'm Hona Liu from Beijing Normal University. Yeah. So thank you very much for the nice talk. So I'm just wondering, so from my own personal understanding, I think I mean, from the experimental point of view, maybe the main challenge is how to generate this resonance state. And for example, in nitrogen 9 case, you use this 3 proton, 1 neutron, 1 proton, 3 neutron removal process. What do you have some estimation for the cross section for such process? And in the future, if you want to do this, for example, silicon 20, and I mean, what is the order of magnitude of the cross section? What will be the necessary beam intensity for this?
Actually, yes, I don't remember the number. So
the order of magnitude will be
yeah, I think it's like a fraction of a millibond. So we started with oxygen 13 that's here, and we created that. We actually, the numbers aren't that much difference. We created fluorine 13 by a charge exchange reaction, and the cross sections are very similar for doing that and doing this. I think in this case, if we were to make silicon 20, this is a 2-neutron knockout. That's probably a couple of millibonds.
Yeah, in the neutron-rich set, if we knock out 2 protons, the cross-section will be in the order of 0.05 millibar. So then I'm wondering what will be the cross-section, 2 neutron removal cross-section in the proton-rich line.
5. Yeah, I guess there's some questions. We looked at so there's Gata-Tostevan systematics for knockout. I don't know if you're familiar with them. What we found, and so you can calculate based on the systematics what the cross section would be for oxygen 13 to oxygen 12. So that's single neutron knockout, and we found knocking out to these unstable resonances, the cross section was down by factor of 2 or something compared to those systematics. It's interesting that we made oxygen 11 in the same experiment, and the cross section for oxygen 11 was about similar to oxygen 12, which is of the order of a millibond or so.
That's interesting.
So that's interesting. We don't have a lot of systematics for two neutron knockout. That would be nice to get. We've never seen we never done an experiment where we've seen a 3 neutron knockout channel. Presumably they're produced at some level, but much lower level than we see here. So yeah, maybe I could figure it out. Remember the magnesium 18? This one was made from a 2 neutron knockout from magnesium 20. I don't remember if cross section was given in the paper, but we got quite a reasonable amount of data from that experiment, so I think it was not too small. But yeah, you're right, of course. Yeah, this sort of knockout from oxygen 13 to nitrogen 9, it was small, but it's not that small for us to do measurement. So you could think of doing that for other cases.
So is this related to those spectroscopic changes across the drip line, I mean the cross section?
Yes, that's right. So yeah, not only did we find that the cross sections was low, but
okay, thank you. Yeah, thank you.
Yeah, there were calculations that showed that the spectroscopic factors associated with removing, say, a neutron to a proton unstable state were smaller than you would typically get in the standard shell model description, and so that contributed to the low measured cross sections.
Yeah, that's very interesting.
But it still is interesting that you got such a large cross section for oxygen 11, which still don't quite understand.
Any more questions? So may I ask that in Florence 13, you mentioned that I mean, how do you assign the spin, and why are you sure it's not a ground state but the excited state?
Oh, okay, well, it's just based on a prediction, a theoretical prediction. So we don't know, of course, from the experiment. Where is it? Yeah, so this is it here. So yeah, so invariant mass. to assign spins, especially these charge exchange reactions, it's not clear that we have any information on the spins. So the only reason we assign this as the first excited state is because that's where Terry, Fortune, and Raymond Sher predicted the first excited state to be, and their prediction for the ground state was here. So, of course, if their prediction is wrong, then this could be the ground state. Of course, you could look at other predictions for the ground state. For example, the atomic mass evaluation. And it also predicts that the ground state is sort of in this region here. So we tend to think it's probably a good guess that this is not the ground state and but an excited state. How do we get assigned spins? Well, at least in knockout reactions, you can, if you have enough events, you can select them so that there's spin alignment. And if there's some spin alignment, then you can make some statement. Also, in knockout reactions, the width of the momentum distribution of the parent fragment. So say we knock out a neutron to oxygen 12, and we look at the momentum distribution, the longitudinal momentum distribution of the reconstructed oxygen 12 fragment. The width of that gives you some information about the spin of the nucleon knocked out, whether it was an S1/2 or P3 half or something like that. So one can get information about the spin of the resonance that way. But especially like nitrogen 9, I don't really know that we could measure the spin I mentioned. It's such a complicated thing that we have very little information about the spin.
I see. Yeah, that's very interesting because if the ground state is 1/2 plus, maybe it's corresponding to a very wide peak because it's S wave, right? And or even a anti-bounded analog state. I don't know. And I looked at the mirror nuclear existence. So the ground spin is also not very certain. I'm not sure if there's a symmetry breaking in this case.
Oh, so you say they could be different. Yeah, that's that would be interesting. Yeah, I guess I think in projectile fragmentation, if you have enough statistics and you select the velocity, reconstruct the velocity of the nitrogen 9 to be on the extreme edges of the experimental distribution, then in such cases, I think some recent experiments have shown that you can get spin alignment. And if you can get some spin alignment, then typically, you know, for instance, if nitrogen 9 decays to carbon 8 by emitting an S wave, that should be isotropic. But if you could, for instance, align the spins, and if the spin is not, if it's not an S wave and you align the spins, then maybe you could see an angular distribution in that step.
Mm-hmm. Yeah, thank you. So any more questions from the audience?
Can I have one more?
Yeah, sure, please.
So I'm just wondering, because in the beginning, Charity, you mentioned the expectation. So for the definition of the resonance, the VDIS has to be smaller than 3.5 MeV. So I mean, is there any theoretical prediction where the edge of the nuclear chart will be with the resonance VDIS smaller than 3.5 MeV?
No, not that I know of. Yeah, that would be an interesting theoretical exercise. Of course, I'm not a theorist, but it would be interesting to just go along the chart of isotopes and make such a prediction. I realize it's not a simple thing, of course. I can quickly show you. I was going to show this slide, but just quickly show, where is it? Oops. Oh, yeah. You can see how fast things are coming. So if you look at some of these evens, so oxygen 12, that's this guy here. That's with like 50 keV. But you go to oxygen 11 and we didn't isolate oxygen 11 ground state that well, but through theory and experiment, we think it's like 1 MeV. So we've changed the width by 2 orders of magnitude and going from here to there. And even going 1 order of magnitude extra will well be on this 3.5. So it may be that oxygen 11 is already at the edge. And you can look at some of these other chains, and you also see that the width is just increasing extremely fast as you add more protons on here. But that's just sort of hand waving just to say that probably the edge is pretty close. But you're right, it would be nice to have a theoretical calculation predicting where this edge was.
Yeah, and because from the presentation, I see all the theoretical curves with some assumed spin parity. It could describe the data rather well. So because in such open system, although we see very exotic decay pattern, could we say something, for the nuclear structure in these, in these open quantum systems?
Oh yeah, okay. So I guess I'll mention. Okay, so these correlations, in principle, have information on the nuclear structure, and so in oxygen 12. The 2 valence protons, there's some probability of them both being in the second s orbital or in the we're both in the p1/2 orbital, and of course they couple to 0 total angle momentum because oxygen 12 ground state is 0. When you so in Simon-Wang's calculations with the coupled channel model, basically what gets out are the S1/2 protons, because the P-wave protons have an extra centrifugal barrier which stops them coming out. Okay, and so this distribution you see then is the distribution you expect for emitting 2 S-wave protons. Now the next heaviest 2-proton emitter is neon-16. And neon-16, the 2 valence protons could be now in the they could be both in the S1/2 or they can both be in the D5 halves. Because the 2, when they're in the D5 halves, there's a much bigger centrifugal barrier stopping them coming out. Right? So they also come out, are supposed to come out in the S1/2 orbit. And if you look at the correlations from oxygen 12 to neon-16, they're exactly the same. And so this correlation pattern you see is indicative of S1/2. So it's telling us that the 2 S1/2 protons are coming out. Now another interesting thing is in carbon 10 is the mirror boron 10, which has a very strong deformed band. So the band head is 0+. And so no one's ever seen the 0+ band head in the mirror in carbon 10. And we found the state in carbon 10 that 2-proton decay. and it had the same correlations as seen in oxygen-12 and neon-16. And so that meant that that state was emitting two protons, two S-wave protons. So the two protons were not taking away any spin, and it decays to beryllium ground state. So that meant the state we're looking at was a 0+. So it was this excited 0+ state. So we were using these correlations to tell us about the structure of nuclei. And I think that can be done in other cases as well.
Yeah, because when you for example, for this 5-proton decay, when you know it's decay process, I think you may have some ability to constrain the binding energy, because you know if it decays via this, the energy has to fulfill the condition. Yeah, maybe you can put some constraint on the binding energy of the intermediate state. I mean, for example, in previous 3 slides, there is no page number. Yeah, the previous slide.
This one or this one? Which one? Oh, sorry, this one?
Previous, upper. Yeah, that one, yeah. For example, I'm wondering, so if you know it's decay process, because in such case, this lithium, because lithium 5 plus proton, the energy and its width has already been well determined. But if the intermediate state is not well determined, if you know it's decay process, could you say something?
Oh yeah, actually, in all these states beyond the proton triplet, I said, are prompt to proton emitters. But when we look at excited states for more regular nucleus, we see a lot of sequential two-proton emitters. So we do see situations like that. And you can look straight at the correlations and see that they're sequential. They have very clear signatures. And so, yeah, you're right. And if you didn't know what the intermediate state was in such cases, yeah, the correlations would tell you. So, yeah, these correlations can be quite powerful.
Yes. Yeah, I see. Yeah, thank you for the detailed explanation.
Sure.
So, any more questions? If not, let's thank Professor Charity again for this very nice talk. And so the seminar is over now. And see you next time.
Okay. Thanks for inviting me.
Thank you for joining this open seminar. Thank you. See you.